A warm greetings to one and all present here. Myself, Selvamina, Assistant Professor, Department of Computer Science and Engineering of Dr. NGR Education and Research Institute. It's give me immense pleasure to welcome you all today of 6 days virtual faculty development program, day 4 on transformative approach in computing paradigms, machine intelligence and quantum computing. Organized jointly by Department of Computer Science and Engineering in association with Center of Excellency CMD and Department of Cybersecurity of Dr. NGR and Educational and Research Institute. So today we are privileged to have with us Dr. Justin Varghese, Professor CSE, GITAM University, Bengaluru. To introduce us, sir, now I invite Dr. Kumanan, Professor, Department of CSE, to give me the brief introduction about today's speaker. Sir.
Oh, thank you, ma'am. So, good afternoon, one and all present over here. It's an immense pleasure and I take a privilege to introduce today's speaker, Dr. Justice Varghese. Good afternoon, Professor Dr. Varghese.
Good afternoon.
So, Dr. Varghese, Justice Varghese received a MTech degree in Computer and Information Technology from Center for Information Technology and Engineering of Mannorbudem Sundanar University, Tirunelveli, and PhD in Information Technology, Computer Science and Engineering from Mannorbudem Sundanar University, Tirunelveli in the year 2008. He received the Best Paper Award at IEEE International Conference on Advanced Computing, NIT Surathkal. He has published 58 papers in referred international journals, proceedings, books, including the IEEE IET image processing journals and many other ISI, SCI index journals. He has presented over 15 IEEE international conferences, including those conducted in India, Italy, KSC. He served as a resource person, session chair, organizing and a editorial committee member of various national, international conferences, journals. He also served as a reviewer of many reputed journals, including IEEE Transaction on Fuzzy Systems, IEEE Trans on Industrial Electronics, IEEE Signal Processing Letters, IET Image Processing, and elsewhere signal processing journals. Presently, he is a co-investigator of major research projects funded by the DRDO, Naval Research Board, India, and he is working as a professor at GITAM University, Bangalore, India. Also, he is guiding 4 PhD scholars. His research interests including a signal and image processing, visual perception, mathematical morphology, and digital watermarking, fuzzy logic, and pattern recognition. With a few notes, I welcome the Dr. Justice Varghese. Take over the session, sir.
Very good morning to all of you, and especially Kumanan sir for welcoming me and giving me this opportunity to have a session. So let us start the session. Okay, I also thank MGR University for this wonderful event. So let me share my what we call PPT. Okay, so that's great. So what today I'm going to do is I'm going to teach you the basics of what we call CNN deep learning. And so how it is working from a very scratch. Okay, so that anybody without any background also can understand what is the things. So let me start with what we call the basics of neural networks, and then coming to CNN, and then I'll teach you how to what you call make your own neural network, and how to make publication over it, and how you can change the architecture of the neural network. No, that is a CNN, and what are the ways it is applied, all these things, basics I will be teaching. So let us start the presentation. So I'm not going to spend much on this, and this is the biological neural network architecture where you will find three basic things. One is the dendrites, soma, and axon. So what it is, so through dendrites, it will accept the signal, and then soma region will process, and then it will be transformed to other neural networks using axons. So artificial neural network basically is mimicking the human biological neural network system. This tree I'm skipping for the time. Okay, so you can go to the any of the lectures or something. You can just find it out. So let us start with the basic of neural networks. Which we have input layer, we have output layer, and we have hidden layers. Okay, so this is the basic things, and each of these neurons are interconnected, and every neurons, every inner neurons will have a bias connection. So, and how it will work. So let us take a single neuron, and then let us work it out. Say here we have the inputs, and here we have the bias. Here I made it as W0 as the weight associated with the bias. Okay, so and these are the weights. And first thing, computation for a neuron is first we'll find out the net value. Net value is nothing but for each of one x1 w1 plus x2 w2 plus etc 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 xn wn, correct? Plus the bias. So here it is w0, correct? So this we call it as a net. And over it, we will apply an activation function to give the output. So this is the basic working of a neuron. Okay? So having said this, before going to CNN, let us have a basics of what you call the terminologies used in the neural network system. So first is training. What do you mean by training? So you are trying to, suppose it is a supervised training, means we already have to train the neuron with label data. Which means we already know what is the output. We try to train the neural network. Okay, so unsupervised training means we don't know what exactly, we don't have labeled data. And in the case of reinforced, we will be having a balance. Okay? So next term we need to know is learning rate. Learning rate is how decides how fast your neuron is going to learn the things. Okay. Then we have the another term called the epoch. Epoch means you have the entire data set. Okay. Each of this, what you call, so one epoch is considered to be whenever your entire data set is processed once. Okay. So which means all the images or data, whichever it is available in your training data set, it has to complete one time entire. Okay. So whereas iteration means you may split the entire data set to different batches. So in order to complete one batch, we call it as one iteration. Right? Then we have activation function. I already told you in the previous slide itself. Here, after finding out net, we will apply the activation function. So here only, so this net, what we are calculating is a linear combination, whereas this function, activation function, is a non-linear entity most of the time. Okay. And after finding this, okay, output, if it is a supervised learning, we know the output, right? We have the labeled data, correct? So for this inputs, we know what is output. So that we call it as in this case, I know you can use any notation. So let us, if you take the actual output which is given is y cap, then you can take it as y. Okay, so you have to find out the what you call the error in here. So that error function which we are calculating, sometimes we call it as the objective function, or sometimes the loss function, correct? So what is the error? So that error we call it as a loss function. Here we have many error functions. I will detail it in the forthcoming slides. So starting with the different activation functions, say the basic function, which is sigmoid function. In sigmoid function, the value will be in between 0 to what you call, it is a non-linear function. From its value will be in between 0 to 1, correct? So 0.5, 0.2, 0.3, something like that. Similarly, the other function which we may use is tanh function. Okay, the tanh function will give you a value in between -1 to +1. Okay? So here coming to it, because any activation function which we want to make training need to be what you call derivable. Otherwise, it will vanish. Correct. So this function, all these functions are derivable. So it will be very useful when we discuss the gradient descent concept. Correct? So now the derivative of this, suppose if you make it as sigma of x, so the derivative will be sigma of x into 1 minus sigma. Okay, so this also you need to remember when you when you want to detail the study of neural net. Similarly, for this one, 1 minus, if you make it as y means y squared, what do you call x? So you can make ReLU function. What it does is it will cut the negative output. This is basically used in CNN, correct? The inner layers of CNN, we use ReLU function. So here what it does is, if it is the derivative also, x derivative with respect to x is 1, correct? If it is 0, it will be this one, correct? Similarly, leaky ReLU. So here what we does is we cut completely all the negative values we cut. But here we provide some, okay, say 0.1 times. We will just reduce the value. That's it. So that time this will become alpha. Similarly, we have softmax functions. Okay. In the softmax function, basically we use when we use classification. Okay. And the output neuron activation function as softmax function, it will provide a probability. So you can see that here. For each each output, you are just summing up the thing, which means you will get a point value. Okay, so which means it will be, if you add all the what you call output neuron values, you will get 1. So that is why this is a probabilistic function. Whichever neuron provides a maximum value, that class only we will assign. Okay, so its derivative also given. Okay, so these things are basic. So coming to the thing. Let me once again go to these things. Sigmoid function when we can use, when we need an output in between 0 to 1 as the output of a particular neuron, we use a sigmoid. When we use tanh function, when we need an output in between -1 to +1. Correct? So ReLU function, we want to cut the negative values. Okay, basically in CNN we use. And leaky ReLU, sometimes if we want to consider negative values also, that time we will go for ReLU. Okay, softmax function when we will use softmax function to ask the output neuron for classification purposes, which means softmax function give you what you call a probability. We want to find out which class have the highest probability, correct? So that class we will assign. So softmax is used as output neuron activation function for classification. So now let us go for different loss bar objective function. Okay, loss function and objective function. I already told you, your neural network with some given weight will produce an output, what you call y cap. Okay, for a particular neuron I, and where the actual, which we know, okay, the correct value, we call it as a y. So mean square error means what you do? You actual minus what you call what you get, the whole square divided by total what you call total number. Okay, so that is what we will do. Correct. So this is the mean square error. Similarly, mean absolute error, we will find out the absolute value of it instead of square. Correct. So mean square error, if you want to use it, suppose if you want to make a regression problem, we will use mean square error or mean absolute error. say you want to predict a value in between 0 to 100. Say, for example, a cement construction, what you call strength. So if you want a value in between 0 to 100, 99, 10, something like this, you can use mean square error function or mean absolute error. So, okay, so here, instead of we can have another function also, which is called the squared error. Okay, so in this case, this 1 by n will go away. So suppose if you want to make a binary classification, means yes or no classification. Suppose a medical image is affected with cancer or not. Okay, so in that case, it's a binary class. In that case, you can use binary cross entropy loss function. And suppose if you have n number of categories, correct? N number of classes. In that case, you have to go for categorical cross entropy loss. So that is the problem. So I already told you, you have to be familiar with this. Where we use mean squared error, so it is used for a regression. So it will penalize large errors. Okay, so because it is squared, correct? So mean absolute error robust to outliers because it will not go much value like this, correct? So both of this are used for regression purposes, binary cross entropy, binary classification, and here for multi-class classification, we use cross entropy, correct? So now let us go for the optimization techniques, correct? So let me open a paint. So just let me put it more. So suppose you are just suppose you have an objective function, something like this. The basic thing what we do is for is stochastic gradient descent. Okay. In stochastic gradient descent, what it does is the theory. So let us go to the neuron. Here we have the output. After output, we will calculate the loss function. Correct. So what we do is for any weight, suppose if we take W1, so the weight update is, if it is gradient descent, it is in the opposite direction of the gradient. So in this case, suppose loss function is L theta. Suppose your loss function is L of theta. Okay. Okay. So what you get is for updating the weight, the derivative is calculated as partial derivative of the loss function divided by the with respect to that particular weight. Correct. So this is the thing you have to remember. So that term only I am making it here. Correct. So what it is? So the weight new is equal to the weight old, whatever weight we had, minus a learning rate. I already told you what is learning rate. What is the value range? 0 to 1. 0 means no update. 1 means full update, which means it will convert fast, but it may prone to make mistakes. So normally we will select it as something 0.01 or 0.001 something. So slow learning will give you better accuracy, but it will take more time. And then this is the partial derivative. What is this partial derivative? Partial derivative is the derivative of the loss function with respect to the weight. So here in gradient descent, what we do is we will for each sample we will take. Let me copy this to let me make this to the paint so that it will be. So we take the first data, correct? It is a label data, so we know what is the output is there. So we will give the input, correct? The neural network will calculate the net, and it will give you the output, and it will calculate the loss function, whichever may be the loss function. Okay. So let us take multi-class cross entropy, okay, function. And then with respect to that, what we do, we will calculate the, what do you call, that loss function. We will derive it with W1, correct? To update this. So what will be this W1? W1 is equal to W1 new is equal to W1, whatever value previously we have, minus eta 0.01 or something you can make, multiplied by the derivative, correct? So this will be done for each data, correct? First data, first it is gone, and then with the same thing, we will apply the same data until some errors is minimized. So like that, we will process for all data one by one, correct? So that we call it as the, what do you call, the gradient descent. Stochastic gradient descent means we want to update the weight in a single basis. Okay, so first data, update the weight, and then second data, update the weight, something like this. Gradient descent will do. In that case, what will happen? There will be more oscillation. So in order to reduce the oscillations, what we do is we will go for stochastic gradient descent, where what we do is as a batch only we will make the updation. That is the only difference between the studies. Okay? So here we will make the entire data set into different batches. I already told you when I explained to you the epoch and iterations. Okay, one iteration denotes one batch, correct? Whereas epoch denotes the entire batches, completion of entire batches, correct? So now what we have is, say, suppose if you have a function something like this, so this is the minimum loss which we have. Okay. So the first one, stochastic gradient, okay, or what do you call simple gradient descent, it will one by one, it will come here, like that, it will come something like this, one by one, it will come. Now we have the next one, which is called the momentum optimization, which means suppose we are at this position, correct? Correct? At this position, when we reach this position, we also know that what is this position, correct? Which means we are now previously we moved something like this, and now we are moving something like this. So which means in the same direction we are moving, correct? Which means so the stochastic gradient descent slowly it will convert. So here, if the model training moves in the same direction, we add something from the previous source, which means it will previously if your normal gradient descent comes here means your momentum will come here because something here also we are adding. So which means you will get a faster what you call optimization. Correct? Understood what it is? Hope you understood. So here what we'll have, we will add a beta times to the previous what you call the gradient direction. Correct? Now we have one more thing, so which is called the nestro. Okay, so NAG. What NAG does is it not only does this, but suppose if you are here, it will make a look ahead, which means if it is going to be in the same direction, it will give you add little more here. Okay, suppose here means it will not add much, it will subtract. Understand? So which means before you jump in energy, you look forward to see whether we need any updation or not. Right? So the next type of optimization is what you call now RMS probe. So in this case, now what we are doing is we will here in this all these things we have constant learning. Correct? In RMS probe, according to the weight value, if the weight value is very high for a particular neuron, so that weight we will reduce much. Whereas if the weight value is or the gradient value is very less, we may give a what you call higher learning rate. So which means for individual weights, it will adaptively apply what you call different learning. So that is the thing here. And finally, ADAM is a combination of this momentum optimization and RMS probe. This you have to be very familiar with. Then only we can learn the thing. So simple gradient descent, what it is, let us conclude what it is. Simple gradient descent means what? It will, what you call, calculate the derivative of the loss function with respect to the weight, and it will subtract from the current weight for each data. So here what it is, it will be applying for batches. Momentum means what? If it will add some previous direction, previous value which we have, previous movement, some we will add here. Correct? Here means, in Nestro means we will first look to the, like this. So if it is in the opposite direction, we will subtract. So something like this we will look ahead and update. So that is our Nestro. And we have the root mean square, what you call root mean square propagation, or RMS probe. So in this case, what we do, we will make different learning rates, correct? Adaptive learning. ADAM is a combination of both momentum and, correct? So gradient descent, what it is very simple, and it will make high oscillations. Stochastic gradient descent, oscillations it will reduce, but it also will give you faster training. But momentum means it will very fast, it will optimize. And here means it will adaptive learning rate, it will make the better convergence. And ADAM is what it is a combination of momentum and, correct? So we studied activation functions, its derivatives, loss function, and what you call optimization. Now, after this, so after completion of each iteration or each epoch, we need to check whether our model is going in the right direction or not. Okay, so otherwise we need to make some adjustments in the hyperparameters. Okay, in any neural network there is two types of parameters. One is the parameters and another one is the hyperparameters. In the case of parameters means the weights and the bias, we call it as the parameters, and hyperparameters example is our what you call our learning rate. Correct. So our learning rate we need to update. So that's why we will make validation after completion of each batch. That is after completion of one iteration or even after completion of one epoch. What we do, we will supply one unseen data, and then with that we will correct the learning rate. So that process we call it as the validation. In validation also, we can have basically four types of what you call validation. So first is holdout validation. In this case, what we do is we split the data set to training data set and testing data. In between, we are not going to do anything. K-fold validation, cross validation means what we do is we will split the entire data set into K different folders. Okay? And then what we do is we will use K-1 folders for what you call training, and that other one remaining one fold for what you call validation, correct? So here, stratified K-fold validation means this randomly we will set the data, correct? Say, for example, suppose if you have 100 records in the data set, so if you make it as 10-fold, what will happen? 10, 10, 10, 10, you will make it, correct? As different batches, and 110 we will be using for validation. But in the case of stratified K-fold validation, what we do is we will what you call suppose you have 5 classes, equally we will try to split, correct? So that is why class distribution training, class distribution test. So accordingly, we will make the K-fold. Okay. So leave one out cross validation means this is basically used for research and what you call performance and analysis purposes, where what we do is the data set number is equal to K, which means suppose your data set is 100 data we have, label data we have. So our k is equal to n, which means 100, which means 11111 we'll different combination we'll make. Correct. That we call it as leave one out, cross validation. Correct. So, and finally, one more terminology we need to remember is the regularization. Okay. So when your model is very complex, or when your what do you call, when your model could not learn much, okay, so or no, there will be a situation called overfitting and underfitting. Underfitting means if the model is not complex enough to gather the information, it will be what do you call, it will give you what do you call, it cannot what do you call do the correct prediction. Overfitting means for the training data, it will give you 100% result, but for the testing data, it cannot perform. Okay, so it will due to the model complex. So how to deal with these kind of overfitting situations? We have methods called regularization. In the case of regularization method, the basic one we use is L1. It's nothing but our absolute error. Correct. So what we do is we will penalize the what do you call the weights. Okay. So if the weight is unconditionally growing, what we do is that is one case of what you call overfitting. So that time we will penalize the weight with what you call some function of the absolute error. Correct. The gradient is too large. L2 means it will be squared, what do you call squared weight difference. So in this case, there will be a smoothness because a squared function always will be a what do you call something parabolic function. So something like that it will come. So there will be smoothness. Dropout regulation means randomly we will switch off some of the neurons. Okay, so this will be very, very useful. Okay, so when we use what you call CNN, this dropout regularization, and early stopping means we have validation, right? After completion of one epoch, if you have one validation, you know what is the current error, correct? Current testing error, correct? So next epoch also you have the error. If the error, normally what the error should reduce, correct? At some point, if you find that the error is increasing, which means what it is, the model is starting to overfit, correct? For the training data, it is giving good result, but for testing data, that is a validation data at this point, if it is giving little more error means its error is increasing means from the previous epoch, if it is increasing means you can identify that the model is going to overfit. So that time what we'll do, we will stop the train, correct? So this is one way of regularizing. Other way is, so the model overfits due to the lapse of variety of what do you call training data. So in that case, we use data augmentation. Data augmentation means, so if you want to increase the data set, what you do is you may flip, you may make mirror effect, you may make the shearing, all the geometric transformation you can apply for if it is images, correct? So that kind of thing, artificially we will generate new data set from existing data set. Correct? So increase the data. So these are the things. So what are the things we need to remember for a neural network? So let me go to the previous thing. From here, we'll find out first we'll provide the input. The neuron will find out the what you call net value, and after the completion of the final output neuron, we'll find out the actual output. We will calculate the loss function. According to the loss function, what we do, we will make the back propagation. Back propagation means how to do it, how to update the weights. How to update the weights? Either any of the optimization methods we use stochastic gradient descent, or what you call Adam method. Okay, so all these methods we discussed, and finally, to regularization also we discussed, validation also we discussed, and how to give the data set to the input, that is called the what do you call what do you call we this is validation, how to give the input for validation, that also we discussed. So let us now go to backpropagation. I already told you, you will find out the net, and then using gradient descent or any of these methods which we discussed, we will update the weights. Correct. So this is the process of what you call backpropagation. So with this initial half an hour, I feel that I have given you an introduction to the working of neural networks without making much complexity of mathematics. Correct. So now coming to the difference between the shallow learning or neural network based learning and the deep learning based learning. Okay. So fundamentally, in the case of deep learning, you will have multiple hidden layers. Okay. Large number of hidden layers. Your neurons also will be more. Okay. And fundamentally, the difference is in the case of normal learning, what we do is we have to, suppose if we want to identify a person by face recognition, in the previous case, if you apply a shallow neural network, or what you have to do is you have to extract the features manually by using handcrafted filters and then give that thing as the input to the what you call the neural, correct? But in the case of deep learning, there is no need of any feature extraction. The neural network itself is capable of extracting the features, correct? Or applying the filters in the case of images, correct? So CNN is an example of deep learning methods where we does not require any feature extraction, manual feature extraction. Say you give the input image, it will classify whether it is output is outdoor or indoor or whatever it is. Correct. So for that, the initial layers, initial layers, we call it as the low, it will extract the low level features. So in the case of images, you understand there is two types of filtering. The first type of filtering is called low pass filters. In the case of low pass filters, we apply low frequency. You will allow only low frequency. Low frequency means the content of similarity. There we'll get the what you call anything which is smooth, which does the smoothing. We call it as a low pass filter. So whereas high pass filter, it will find out wherever it is differences, the edges, corners, all these things, high pass filter will get. So whenever we move from, from initial layer to the outer layer in a CNN, it will extract features from low level features to high level features, like what you call mid level features, high level features of trainer, and finally, using this, we make the classification, correct? So deep learning versus ordinary learning, what I told you here, suppose if you want to identify whether it is a car, you have to do the feature extraction using image processing techniques, and then we will give to any neural network or any machine learning technique to classify whether it is a car or a not. But in the case of deep learning, directly you will give the image as the input to the deep learning network and get the output as car or not. So because we are going to CNN, we should know what is an image. So image basically is a function. Okay, so it is a light intensity function. F of xy is equal to I of xy into R of xy, where I is the illumination and R is the reflectance. So amount of light it is produced to illuminate, that we call it as illumination. From the received illumination, how much it reflect back, that is called the reflectance. Reflectance is in between 0 to 1, and illumination can go to any value. So let us see what is convolution. Before going to convolution neural network, we should know what is convolution. Okay, so there are two operations in image processing. Okay, so let me write any array or something. Okay. So let me make it a little more bigger. So some values. 6. Okay. Suppose if these are the values here. Okay. So these are array. Okay. Array of values 5, 7, 2, 7, 3, 6. Correct. So suppose if you have a filter here, suppose 1, 0, 1, 0, minus 1. Okay. So first, let us see what is what you call correlation. Correlation means if this is a filter function, you have to apply it without taking mirrors. As it is, you have to apply. Okay. Okay. But if it is what you call convolution, what you have to do is you have to take the mirror of it. So in this case, what is the mirror of it? Minus 1, 0, and 1. Correct. So now what you have to do is you have to take this. Okay. You have to place here. Okay. And here, what you have to do is here at this case, so here you cannot apply. So what you do, you have to make padding. Padding means here you add part. Okay. So here also 1, 0. Okay. So now you can. So here also you can make it as some 0. So this we call it as the zero padding. So you can make different types of padding, symmetric padding. In the case of symmetric padding, you will be padding with 5, 5, 5. Okay. Here also 5, 6, 6, 6. Correct. So now you are applying here. So what is the value? 0 into 1, minus 1, plus 0 into 0, plus this one. So what is the value here? The value is 5. Correct. Then what you need to do is you have to, what you call, move this to next place. So what is the value? 0, 0, and 7. So here, what is the value now? Here, the value is 7. Correct. Now, what is the next step? You have to, once again, move this to next place. So here it is minus 5, 2. So what is the value? Minus 5 and 2, what is the value? So it is minus 3, correct? So like that, you have to move until here. So at this place, what do you get? If we move it here, what do you get? Minus 6 is the final one. So here you will get dot, 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 dot. So final value is your, what you call, minus 6. Correct? So 6 into minus 1 plus 0 into 0 plus 6. So this operation, we call it as the convolution operation. Whereas correlation means you need not make the flipping. Directly you can apply. So that is the difference between convolution and correlation. Correct? I'm not going into the formula of it. Clear? So having said this, so that is what here it is. So this is the correlation operation. Here it is plus, here it is minus, means it is the, what you call, convolution operation. We have a mirror operation, that is a minus minus here, means it is the convolution operation. This is the correlation. So how it works? Let us make an example. So here, suppose if you want to apply, so the same way which I explained there, take entire mask here and then apply here. So what will happen? 1 into 1 plus this is a typical average filter. Sometimes it is called the box filter. Okay. So previously we were using this. So now apply this 1 plus 5 plus 10 plus all these things divided by how many are there? 1 by 9. So you'll get the average of this and that value is placed. Now what you do, you will apply at this position as a center, correct? So this area it will cover. So all these values are added and then divide by 9, we'll get 7. Now here, here you will apply. So here you will apply means this much value, you will sum it up and divided by 9, you will get average value. So then you will apply here. So like that entire image you will apply. So the same only here also. So average filter at this area, find out the average. Now what you need to do? You move to the next place. Next place is this, correct? That is average of this one. You place it here. Then you move to here. You will find, and after that you will move to here, correct? So like that, move everywhere and fill up the value. So this is how the filtering operation or the convolution operation works. Here, no need to take any what you call mirror. Why? Because it is a symmetric mask. If it is not a symmetric mask, you have to take the mirror. Correct. So different filters. I already told you. Low pass filters, what it will do? It will make the smoothening. Correct. So if this is the input image, we make average filter, it will make the smoothening. Correct. If you apply a high pass filter, what it will do? It will allow only the high frequency component. So you will get the edges, all this. Correct. So basically, these high pass filter outputs are useful for image class. So these are the different things. Okay. So another thing is, which we know, one more term we will be studying here. Here we call it as the pooling or subsampling in the wavelet or something. When we study, we'll find it. So now, what is this? Reducing the size. So what is the need of reducing the size? We need to process only less number of pixels, correct? So what we will have, suppose this is mn size, m rows and n columns. Suppose if you reduce it by 2, no, scale of 2, what you get is m by 2, n by 2. So which means 1/4 the size of this image, correct? That is what we call it as a pooling. Okay. So in pooling, let us see. So suppose 2x2 pooling, if you apply entire thing. So suppose if you apply the max, there are many types of pooling: max pooling, min pooling, average pooling. But normally we use max pooling because we need to extract the most prominent values. Correct. So that's why we have 1 here, 3 here, 4 here, 2 here. We find the maximum of all these things, we will get it. And similarly, this 2x2. So this is non-overlapping. Okay. That is shifting is 2. So shift first here means 1, 2. So that is the shift. Okay. The stride. Sometimes it is called the shift or the stride. Okay. So here will come 5, 3, 3, 1. Maximum is 5. And we finish the first row. And we from here was the first question. Row also we will make 2 strides. That is first stride, second stride. So here is our system. Find the maximum. Put it here. So this is it. Average means find the average. Minimum means find the minimum. But normally we use max pool. Correct. So I'm not touching recurrent neural network in this because we are using only what we call now CNN, which is a feed forward, which means there will not be any recurrent connections or backward connections. Correct. Only the forward connections here, but we have the backward or self loops. Correct. So in recurrent neural. And hopefully in another lecture or something, if we have time, we'll discuss the recurrent neural network like LSTM, GRU, all this. So convolutional neural network, what it does. So how it works is, so for an input image, previously in this, when we teach, okay, so here, this is a handcrafted filter. Now in CNN, these all things will become weight. The neural network, as the weight is now optimized, similar way, what you call, we need to find out this. Okay. So there is no need of any handcrafted filters. Correct. So that is the idea of CNN. So now coming to the thing, okay. So suppose we have an image patch 36 cross 36, we design the what you call how many filters we need. Okay, so that is called the filtering, and then we have the ReLU layer. Okay, that we let us discuss the entire thing here. Okay. So here we have the image here. Okay, so we apply a filtering. Okay, so a filter here, and then with respect to this, we'll get the value here. Correct. So after this, like that, we'll move to everywhere. All these values we'll be getting. We'll be applying some padding and other things to get. I will explain all these things. Correct. Padding you already know. I already know for the one-dimensional data. I made it. So and then second filter, apply it, and then we'll find out these values like that. We'll go. Okay. So if it is a color channel, means we have not only one image. Okay, we will be having for red, green, blue, we have different types. So in this case, the 3D filtering, we have 3 what do you call filters. Okay, for each one for this. So that is what filter 1 also. Yeah, if it is a 3-dimensional, 3 means 3 rows and 3 columns, 3 into 3 into 3. So 3 filters, 1 for red, 1 for green, and 1 for. So basically, if you want to classify an image to car, truck, or all these things, this is a classification problem. So you will be having what you call the first is convolution. After convolution, what do? You will apply the ReLU. ReLU is what it does. ReLU cuts the negative ones, and then over that data, we will once again apply the convolution and then apply the ReLU. And sometimes if you can define where you want to do the pooling. Pooling means what it will do? It will reduce the size. Correct. Why we need to reduce the size? Or to reduce the process. Correct. So like that, a combination of convolution, ReLU, and pooling, many things you can make it. And finally, everything, the entire data is connected to a fully connected. Right? After fully connected layer, since this is a classification problem, anybody from the batch, can you tell me what will be the output neuron activation function to be applied here? Anybody? Can you switch on the mouse and tell me, on the mic, and tell me which activation function you will use for an output neuron for classification? Can anyone? Or type in the chat box? It is not sigmoid. Here we have to go for softmax. Softmax, what it will give you? It will give you a probability. Correct. Probability means whether car is having the higher probability, so 0.8 or some 0.6 or something, we'll assign the classification to car. Correct. Okay. So that we finished. Okay. So this will be total probability softmax. Correct. Similarly, for this problem, what could be our loss function? What could be our loss function? We have mean square error, we have mean absolute error, we have binary cross entropy, we have multi-class cross entropy. Which one we will use? No, multi-class cross entropy. Why we have multi-class? Here, 1, 2, 3, 4, 5 classes we have, right? So we have to use multi-class cross entropy. Okay. So any optimization, which optimization you will you prefer for this? No. Here you can use any optimization techniques, but normally we will use ADAM, or ADAM optimization is best. Okay. So I feel some of you are listening. Okay, thank you. So let us go to the next. So now many applications, the application, any image classification like disease, medicine, what do you call medical field, or what do you call any sort of image classification, we have CNN. Correct? But if you have what you call anything like video application, you need to have CNN plus one of the what do you call RNN. It can be the traditional RNN or LSTM or GRU. Okay, so this kind. Correct? But for a normal image classification, we use CNN. So let us go to the first example. So I have explained you all the things. So let me open the MATLAB and give you the first example, correct? I will explain each and every what do you call thing. Okay, so let us take a small classification. So I made a small data set, correct? So I made what you call 5 types of moths. Moths. What is the difference between moth and butterfly? There are some difference. So it's not butterfly. It's called moth. Okay. So this is one type of moth. So this moth is called Akatia moth. Okay. So I made 5 classes. I just downloaded because we need to make the training very fast. Correct. So that is why I take very small Python. It will not give you much what you call clarity, much accuracy or something for testing data. Why? Because it is very less number of data. Correct. So for faster optimization, I have taken this because we need to complete 4 or 5 what do you call live sessions on training and CNN training. So that's why I take a small. The second class is something which is called what do you call emperor mode. Okay, so this is called the emperor mode. Different, another type of what you call mode. The third one, this one. So this is called proportion. Okay. So fourth one, it is what you call atlas mode. Okay, so this one is called atlas. In the fifth class, I take it as this type of mode is called Luna mode. So our problem is a multi-class classification problem using CNN. So I feel you understood. I have 5 classes. Each one, the label I have given us 1, 2, 3, 4, 5. So let us see. Now let us define a what do you call a program. I already written the program. So now, so initially the data path. What is the data path here? So this is our data path, correct? So this path only I am going to copy, correct? So this data path I have made it. I feel it is correct only. Okay. So then I am making an image data store. Okay, image data store. Image data store. What I am going to do is with this path, include any subfolder is there. That subfolder also I am going to include. Okay, anything inside this there. The label source is folder names. What is my label? So label source here. Label. What are my label? 1, 2, 3, 4, 5 are the labels I used. So that is why the folder names are going to be the label source. Okay, and I can define my own size. I decided it to the neural network to be size 200 rows and 250 columns of each image. If I decide this, I cannot guarantee that these images, all images are of same size. So what I have to do next, I'm going to resize the image. The command we here which is used is IM resize. Okay? So I have resized, I have read all the images, made an image data store, and then what I am going to do is I am resizing it to a predefined size because input neurons I need to make. Now, then I am going to split. Okay, so here I am going to make only what you call training and validation. Okay, testing, I am just showing in a different way. Okay, I'm not splitting it into what you call for separate data for testing, correct? So here I'm using only this TR images is for training images. This is TST, but it is not for testing. It is for validation, correct? And after that, we'll test, correct? So number of classes. Number of classes, how to find out? How many categories are there for the training images? How many categories are here? Here it is totally 5 categories, correct? So that is going to be, you can even give it as, okay, number of elements. Instead of number of elements, you can make it as 5 in this case. And then layer. So of course, the first layer should be input layer. What is the input layer? What is the size we have given? Any doubt or anything? Any doubt or anything? Okay. Okay. So, okay. Okay. So size is what you call 200, 250 I have defined. Okay. So that is the input thing. And then I told you the convolution tool. There are 2 types of convolution I told you. What are they? 2D convolution and 3D convolution. In the case of 3D convolution, what we will have is we will not omit the 3D component. So here in the case of 2D convolution, what we do is if you apply a color image with a 2D convolution, what do you get? You will get a grayscale image. Okay, that's the thing, correct? Suppose it is 3D convolution, you will get a 3D dimension. That is red, green, and blue also you will get as the output. So now here, what I am going to do is I am going to define the size. Size is 3. 3 means 3 cross 3 filter. Okay. Same like our box filter. We are going to apply a 3 cross 3 filter. How many filter in the first phase? Like that, how many filters we are going to make it? 8 filters. Okay. And padding. Padding same means when I taken the example of the manual convolution in the paint, I made 0 padding. Here it is same. Same means what? same value. So instead of 5, 5 is the first value, means 5 will be padded in the left side, top and below, right? So like so that is symmetric padding. Okay, so that is called symmetric padding. And I named the layer to be convolution 1. Okay, then what I do is I make the batch normalization. I feel I missed that concept. So in the case of batch normalization means I told you we are going to process batch by batch. Each batch completion, we call it as one iteration, correct? So each batch, we are going to normalize by using its mean and variance in the range 0 to 1. All the image value, basically, if it is an 8-bit image, the values will be in the range 0 to 255. 255 means 2 to the power of 8 minus 1. So that is the range. That range will convert it to 0 to 1. But this is, we will make it by batch-wise batches. So that is, we call it as the batch normalization layer, correct? Then we have the ReLU layer. ReLU layer, what it will do? It will allow only the positive values. Negative values, it will cut, correct? It will not allow, correct? So what is the formula for it? Maximum of x comma 0, correct? So all negative will be cut. And then we have max pooling layer. Max pooling means we will reduce the size. Here it is, 2 cross 2, the same thing which we worked out. 2 cross 2, what is the stride? 2. So which means there is no overlapping. 2 cross 2, after this, 2 strides will, right? So there will not be any overlap. So this is okay for you. These 4 things, this is the input layer. After input layer, you have a convolution layer, 2D layer. If you want convolution 3D, you can make convolution 3D. Okay, and then we have match normalization, ReLU layer, and then max pooling. The same thing is repeated here, but with a different. Whenever you go in depth, we will increase the what you call number of filters. When we go from here to here, in the initial cases, we will be extracting low level frequencies. Okay. When we go down, we will go for higher level. Correct. So here also we have how many filters? 3 filters of size. No, 16 filters of size 3 crores. Similarly, we increased here 32. Another this one same only here also, and then here we have the final case. After this, we have the what? We have the fully connected. In the fully connected layer, after fully connected layer, I told you because it is a multi-class classification, we are using output layer neuron function as activation function as soft max. Right? And then finally we have the classification layer, and the name is out class. Correct. So we have given the layer name as out. Right? So up to this architecture, you understand? Now we have to make, this is only for plotting the graph. Okay, so the layers. Correct. So now the training options. What training optimization we are using? SGDM. What is that? Stochastic gradient descent method. Correct. So learning rate initially we set to 0.01. Maximum epochs you can set. Now depending upon your problem, this is we want to make it fast training. So that is why we have given epoch as 70. Okay. And shuffle. Okay. Every epoch we are going to shuffle it. Okay. And validation data, we are using this. We split initially to training and actually test the variable mistakenly I have given, but you can use that. This is a validation data. Okay. So that validation data, I'm using this. And validation frequency means 5 means what? After 5 epochs, I'm going to use one image as validation. Correct? That's true. So it is okay. And then plot. I'm going to plot the entire training process. And okay, so net is equal to. So here what I am going to do is using the train images and the layers, which I already defined here. And then these are the options. The stochastic gradient descent method only I'm using here. If you want, you can use Adam here. And then what we do, and then we are going to make the classification, classify net, test images full. The validation images. Once again, I'm just testing and then finding out the accuracy. Okay, so by valid is equal to test. How much are there? We are going to check it. Okay, so you can calculate the accuracy also. So I'm going to do it. So I can run this. You can use Python also. The same, almost everything will be same only. nothing much difference. So I have given the training process. You can see. Anybody want code or anything? Just contact through your department. So this is the architecture which I just plotted there. Now the training process I'm plotting here. It will end up in fast because very less number of data and also layers are also very less. Only 70 folks I have given. Okay, so you can see that something still will be getting an accuracy of 95% with validation. Okay, so now understood this training process, how to give it. I explained to you every all the aspect, at least rough, you will get it. Now I want to test it, correct? Say I want to test it with an image. Okay, so what I'm already in the here the what do you call here? You can see all the net trained data already it is here. Using that only I'm going to test with one image. Okay, so I'm going to read one image and then okay, so I'm going to read one image and then what I'm going to do is I'm going to classify using the trained net. Okay, so I'm resizing the size to 250 unknown data and then I'm just displaying that image with the label, whether it is 1, 2, or 3. Okay, so let me run this. So all this data, which is used for training and validation. So I'm going to use another data, something say. So let us use this, correct? So this is a Luna moth. Luna moth is of 5th category, correct? So in our training data set, it is the 5th category. Let us see what the neural network will do. So it is predicting it as 5th category. Can you see this? So this correctly predicted, correct? So the first experiment is over, correct? Now we'll go for the next one. Okay. Okay, this is what we studied. And before going that, you need to know how the transfer learning. Transfer learning means we already have many pre-trained network like AlexNet, GoogleNet, MobileNet. Okay, so how to conceptualize it for your need? Okay, two ways you can take it. You can either take the entire architecture as it is without the weight values, weight you are going to train it, correct? Or even say, for example, if it is for a similar task which is already pre-trained, if you are going to use it, then you can conceptualize with the old weights also you can use. Two-way you can use it. Which means transfer learning means what? Already there are pre-trained network that either you are using the architecture or architecture with the pre-trained weights also. Okay? That you are going to reuse it for your application. You call it as transfer learning. So let us see AlexNet with webcam connection also we can do. So I will make it as the final because the network connection may go. So I have only one what you call webcam. Or anyway, let us try. After finally we'll go for the third example. So transfer learning with Alex. Right? So now with the same thing, what I am going to do is I am going to make the transfer learning. So here what I am going to do is the same thing which I explained there only. So here the standard size of AlexNet is 227 cross 227. Cross 3 is the input length. So I am going to resize it to that. And then here I am making it as validation and the same thing I'm going to use it. Okay. And then some random, in order to make display some of the samples. In a 4x4 layout, I'm going to display the images. That's why this is just for displaying the images. And net, what I'm going to use it, which net? AlexNet. You can use any net, AlexNet or what you call mobile net or any network you can use it. Correct. So now the input size, I am getting it from that net only. So, otherwise, if you want, you can make it as 227. The number of classes, the categories of the trained data, which the same data only we are going to use it. Okay. So now only layer we need to change is, say, what do you call AlexNet is a network which has, say, 1,000, what do you call 1,000 or 100? Let me see. Say 1,000 different classes. Okay. So here for me, how many classes are there? Only 5 classes. So I'm going to make it as 5 classes here, categories of, okay. So that 5 classes only I'm going to make it. And I am going to use all the layers of what you call AlexNet as it is, except the last 2 layers. Correct. Correct. So n minus 3. Okay. Last 3 layers only I'm going to use it. What are the 3 layers? Here I have to change the fully connected layer with there. How many classes are there? 1,000. Now I want to change it to 5. Correct. So that is why 5 here. And weight learning factor 20 and bias rate learn factor is 20 I have given. And then I'm going to make new softmax layer. There in the softmax layer, previous fully connected layer is 1,000 means 1,000 output neurons are. Correct. So that's why I'm going to change it according to this. And then finally, we have the classification layer. Okay. So here also what you call the options I'm setting similar to stochastic gradient descent, batch size, maximum epochs. Okay. Initial learning rate, that is 1 into e, e power minus 4. Or you can make it as 0.00001 or whatever one. Validation is I have split there to what you call validation, correct? Then validation frequency is 3, okay, after 3 epochs. Okay, and then I'm plotting the thing, and then finally, what you call I am making classification for entire one thing, and then finally some random elements I am going to take it. How many? Totally I'm going to make it as 4 output. 4 randomly I'm going to take it from the validation set and going to classify and what you call draw in the title, similar to the previous. So let us see what it will happen. Anybody want program or so this is a standard size for this. So this is just plotted some of the samples of the thing, and this is the training I just started. Okay, so I have given only very less epochs, so but it's getting something 94.4, and then some random data I have dispensed. So this is the second type. This is also correct. This is 4th Atlas, and this is the 5th Luna, and this is the first. All classification done is correct. Correct. That is what I have. Correct. Any doubt or something, or making you boring or something? You can tell, please. Okay. Data set. I will. Surely I will send. Okay. So the third one. Okay. The third or fourth, I feel. So next example, next problem, let us go for what you call deep network designer. Okay, so this is very, very important. Say, for example, all of you, can you please tell me you are all faculty members or students or? So nowadays, what will happen is, are you, in that is faculty members or?
Yes, sir. Almost faculty members only, sir.
Faculty members.
Okay. Scholars,
Okay.
sir.
So, say for example, the first question is, in the case of deep learning networks, everybody will ask you, if you send any paper, they will ask you what is the difference between your network and the previous network. Correct? Correct? So this is the one difference, and how your model is better than the other model. Correct? So this is very thing. First thing. And it is very difficult for you to what you call like this. If you want to make coding, it is very difficult to write the code. If the thing, it is very you cannot remember all these things. It is very difficult. So MATLAB, in MATLAB, similarly, I feel Python also may be having, correct? So we have a, what do you call, a tool called deep network design. Okay. So I'm going to that. Visually, you can make graphically, you can design the network and then you can make, correct? Okay. So it came, correct? So any network you have, so these are the, whatever it is warning it is giving, I didn't install it, okay? So only Google Net, SpuseNet, this network only I have installed. Oh, AlexNet also I have installed. So we will use, because this is a simple one. So I am going to design the network, correct? Correct? So the network came. Now let me little zoom in. So can you see this one, or little more zooming is required? So as transfer learning, I told you all these layers I am going to use it as it is. Which are all the layer I am going to change? The last layers, correct? So here you can see here the output is 1000, which means the classes are, number of classes are 1000. I want to change this. Similarly, this softmax. So what I'm going to do is just delete it, correct? Okay. Whatever alteration I can do it here. So which are the layer I have to make it fully connected layer? I just drag this, like what you call, I fix this. And one more layer I want. Which layer I want? Softmax, correct? So softmax or no, RPN softmax layer also you can use. Whatever change you want, you can make it good, correct? So now I have to give the connection here. Automatically it will connect, correct? I just make it, correct? Correct? Now I made the network. And here in my case, how many classes I have? I have 5 classes, correct? I have 5 classes. That's the only change I'm going to do for a transfer layer. Suppose if you want to make change, any layer you can delete, any inception connection you can make, whatever experiment you can make. So everything you can make here. And also, because when it comes, I will explain Google Net also. After this, I will take it, and because that is such a huge network with lots of inception connections, it is very difficult to find out whether you are correct or not. Okay, when you design also. So that is why you have a tool here called analyze. If there is any error, automatically this will detect whether there is any error. So let me analyze the network. So all these things, no warning, no errors, correct? And each layer, how many parameters, how many things, all these things you can see here, correct? Weights, parameters, all these things. Understand, no? Each layer, all these things, there is no warning or there is no, what do you call, errors, correct? Which means this network, you can use it for your need. You can make any changes, you can add layers, you can delete layers, whatever you want. Now, then finally, if you want to use it, you can have, I already told you, transfer learning, you can do it by 2 ways. One is with parameters, you can use it without parameters. Okay. So for me, say this, what do you call, AlexNet, what do you call, being used with what do you call, the pen, pencil, mouse, what do you call, keyboard, all these things. Okay. Now, what do you call? So my data is different. That moth data, correct? So I'm going to use it without parameters. So I click this, automatically the code will come, correct? So what I'm going to do is I'm just going to make it. I already made it. Okay. So I'm going to make this. So this same code. So the entire code I got it, correct? So this is in MATLAB also similar to Python. There is a concept called script and MLX. Okay. Okay. So here Similar to that, you can, your Pythons, you can write text, all these things. But in text, whatever in script, you cannot do that. So let us make it. So where it is, okay, so this code, I can use it. Okay. So what I'm going to do is this code, I'm going to use it. So you can make it as new script, right? Already it is here. Okay. So that code only here. Okay. So this one only I'm going to use it. Correct. So I pasted that code here. Okay. So whatever code I have copied from here and pasted. Okay. And what do you call? So I have made it. Correct. So now remaining all same. Correct. Say this is a path. Everything is you have to make it as standard size, and then what do you call split label randomize, and then this is the code that using network designer we have what do you call using this network designer we have created the code, right? When you make export, automatically the code MATLAB has written, correct? So that code only we are going to use it, correct? Now, if you want any changes, you can make it, say some portion of another network, you can copy here and what do you call construct the new network so that your network will be new, correct? Not from completely different from the architecture is completely different from the other network. Okay. So then the other code only the network layers only I have changed. Okay. So remaining all it is same. So this also I can make, correct? So let me try. Same thing. So you know how to change the layers, correct? Layer architecture of a neural network, correct? Or a CNN, correct? Using that, you can make it. But the fundamental thing which I taught you, what is optimization, what is what is the importance of stochastic gradient descent, loss function. These things are very, very important when you need to. So I'm giving that training, correct? I have given less number of training only, so it will convert very fast. So it will finish now. Okay. So the training is finished. Okay. So now what is accuracy? Let me check. Accuracy is something 65% only it is given because data set is very less number. And also this AlexNet having more layers. Okay. So it will overfit for the less number of data. Right. So understood how to do this. And then let us see a complex network. Okay. So a new network I'm going to make it. Okay. So little more, say, let us make it as Google Net. So how complex it is, you can replace. Right? The deep network designer. How complex it is, you can see. Okay. So let me zoom in. And so any layer. So here also what I need to do, these layers, some of the inception, these are all connection called inception, you know. So what is inception layer? So here we have parallel connections. Why we need parallel connections? Suppose if you make very large network like this, one after one after one after one after sequential network, the gradient descent method when you apply, okay. So when it comes from last layer to 100 to the 100 in between layers to reach the first layer means the weight updation will become smaller. The gradient value will become smaller and smaller, which means there will not be proper updation. So the neural network will stop training, correct, at some point. Correct. So that is why, in order to make, solve that, and also we need the input from the last thing to other thing. If you want to pass, we use the inception connection. Correct. So these connections we call it as an inception connection. So understand what it is? Clear? Or anything doubt means you can ask. So now here also, if I want to make to my application to run, what I need to do? You can one inception, all these things. If you want, you can delete. You can do all alteration. After doing all alteration, what you have to do? Click analyze. It will tell you what are the errors, which are all places you need to make it. There is how you can make new networks. So now, where I want to change, where I need to make the change, I need to. So for this application, I need to. This one I don't want. Here, how many are there? 1,000 output. How many outputs I have? Okay. So simply change fully connected layer. Just drag it. Right. And similarly, we have soft. Just give the connection from here to here. To here. So here we have to change it to 5. Correct. And then just analyze. It will give you there, not be around, because we changed only. We didn't make the changes in the complex areas. Correct. You can try that. Okay, so here is no warning, no this one. What are the layers? All the Google Net architecture, everything is same. So how much big network it is? Correct. If you want to make any alteration here, you can very easily do it. Correct. You can delete, you can add. Okay, so that you can. So your aim should be for a particular problem. Okay, say for example, even this may give less result than our neural network, because this is a complex CNN where ours, we have only limited number of what you call data samples. Correct. So that time our network will perform better than. Correct. So you can make combinations of sequential with this kind of inception network using the network designer, and then you can make your own network. Correct? Clear? Understood? Yeah. So now it is no error. So what I need to do, I can do with 2 ways. I'm not going to make the parameters. I'm just making the live script I'm creating. Whatever architecture here I made, okay, you can create manually your own also. So this network only, it is a very big network. Okay, so this is the layer network. Okay, understand? No, there's a code for it, and this is the inception connections. Correct. I already made it here. Okay, so entire thing I copied here and then I made it. Correct. Understand? No, so that inception connections, everything with the same data set I'm going to make. So understand how to make an easy paper. Somebody want to make a small journal paper or something, what you can do for take a particular application, any medical application, medical imaging, or any classification problem, using network designer, make a better network than any of these networks. Correct. With a combination of a simple thing. So make a combination of what you call any of these network you can make. Correct. So this architecture from somewhere here. Okay. Finally, your result should be little better, and also your number of parameters also little less. Clear? So this is a simple publication you can. So this is also, so the same thing only, I can just run. The options, everything is, I made it same only. Okay, so I need, okay, options, everything. So this all I made it same only. Same network, Google Net. So you now learn how to make your own model, correct? Instead of writing the code, you can go to Deep Network Designer. Then. Anybody, what is the time? 2 to 4, no? It is, correct? Correct? So you can see that
sir.
there.
2 to 4 release.
Okay. Okay. Which means I have 10, right? I have 4 or 5 examples now. The same thing, you can do it with Python also. Almost coding, everything will be same only. Okay. So like that, you can so you can see that at this stage, the validation error is increasing. Okay. So at what you call early stopping, if you apply means automatically here it will stop. Understand? No. So the validation error, once it is increasing means the early stopping will stop there. But still, it is only a spike. And after that, it started reducing. Okay, so finished. Correct? It is going to make it. Because this GoogleNet is a very large network. Okay, so if the data set is bigger, say for example, an Alzheimer's disease data set or something, that itself is 3 GB, 4 GB. It will take 5-6 days to convert at that case. So you have to make use of some what you call GPU based train or parallel computer based. So training stop. So I can use it. No, the same thing. Okay, so here you can see it will not give much better result or something. Correct. Correct. Our model 90 or something we give. So although it is very big, so which means depend upon your application, the architecture need to be changed. Correct. Any doubt in up to here or something you can ask. So can I go to next one? So another when you write papers, people will ask you sometimes to show the activations. Means after training the neural network, say for example, a car, a truck, or any type of classification when you make it. So when you give an input, your activations of individual neurons, okay, will represent the intermediate convolution layers, correct? So which means, so which are all part of the image, which is sensitive for making a judgment that this is going to be the class. I'll show you. So that time you need to visualize the activation. So that we call it as, sometimes we call it as what you call evidential learning. So, or what you call, you have an evidence what it is. Okay, so let us make it. So the visual activation. So I just use AlexNet. Okay, no other net, AlexNet, and I take a natural image. So any image you can give, and then what you call the first layer only I'm going to do. Okay, first layer I'm going to do, and then I'm going to resize the image to what you call the input image. Correct. So this image need to be changed into the size. I feel it is 227, 227. I'm resizing it. I resized it. And then I'm going to take the activations of the particular net. Net is AlexNet, correct? And then I'm going to show the thing in 18. So I feel this convolution layer, I feel 91, 96 are there, but I'm again taking only 8 into 8, 64 activations for the convolution layer 1. This also while writing the paper, they may ask to show the activations. I feel it is already because the picture is so. So here you can see that 88 activations, which are all places actually it is changing. Correct. Actually, this is the image itself is irrelevant. The AlexNet is used for classification of what you call classification of the pen, pencil, mouse, what do you call it? Keyboard, all this. Correct. But the image which I have given is a pepper image. Okay, so this image only I have given. Okay, so that is irrelevant to this classification, but still you know how to. So you can use the function as activations. Correct. So now let us go for what do you call next example. Okay, so deep dream. Deep dream means, say for example, making holistic images. Say for example, what do you call? So suppose if you want to make an image where what do you call some peculiar patterns you have to what do you call promote, which means how the activations will look like. Okay, so it is a what do you call dream-like appearance in the deliberately processed images. Okay, so Google program it is created. So that also we will see. Okay, so what are the things being asked to? So here, before going to that, here we can, if you want any layer, up to 5 layer only convolution layer, we have any layer, we can see the activation. We just change to the layer 5 or 4 or 3 or whatever. But it will give you error, I feel so. No, okay. So you can see this, understand? So this is a 5th layer, okay. So now let us go for the deep dream. Okay, so you will find. So what I'm going to do is from what you call, I am going to take from the layer, what you call the 1/4 channel, 293 channel, all these channels only I'm going to make it. Okay, with that channel, what I am going to do is I am going to make 5 classes. Okay, so I'll show you. Okay. Oh, the training going on. Okay, so what it does is we have told the neural network for the first image. I told no, the snail image. What do you call that activation? You have to make it more prompt. Second one, something tiger or something. Third one, I have given the instruction to for zebra something. So you can see here. Say, there it is. Say the 6 images I told him. So 6 channels. Okay. First one, I imposed now what you call snail, tiger, zebra, something. So that is one type of thing. And one more example we'll take. I think we have time. Yes, we have time. Yes, we have time. And 10 minutes we have. And how to use camera. Okay, so let me switch off this camera. The webcam, I can use it for the program. So I am connecting my webcam. Not only webcam, if you have what you call any IP camera, wherever you want to make it, somewhere in the gate or anywhere, okay, anywhere outside, we can have an IP camera. You can make it connected, okay, and then I'm going to reshape it into what you call the same size, and then I'm going to. Okay, so now you can see this. So it is detecting my image. Okay, so I am going to use the webcam here. Okay, so I'm going to show this as what you call. I can see. Can you see this connected? So it is identifying it as a computer keyboard, or if you show here, it is identifying is it as a mouse? Yes, it's a mouse. Correct. So this is trained LexNet. So your network also you can connect it to something. Correct. Okay. So that is what I wanted to tell you. And then after that, you can use clear the cam variable, which means, right, so it is clear. Now I can connect it. So one more example, if we want to know, I feel I am disturbing you too much. But still, one more example I will make, one more tool also I will introduce to you. That is, sometimes you need to make image-based segmentation or object detection, some type of problems when you work. That tool will be very, very useful. So that is, go to the apps, and then from that, you can select one apps called, what you call, image labeler. Image labeler, video labeler, many are there. Okay, so you can see image labeler here. So you can make an individual project. Say, for example, so this is my image labeler. So I'm going to import the image from file. Okay. So any image you can insert. Say I'm going to make a small application. Okay. It's already been done. Number plate detection or something. Okay. So let us simply show, and I'm not going to use it because it will take time to label the data. Yeah. So I'm going to take some images, just all images. Now it will come here. Now I need to, which object I need to select. So my problem here is to, what you call, select only the number plates. So whenever you have a number plate problem, I want to find out whether, in order to make number plate classification, okay, so first I have to locate the number plate, correct? So for that only, I'm going to make the labeling, correct? So labeling here, I'm going to say, for example, in what I want to go to label, which type? Suppose if you want to make segmentation, like what you call semantic segmentation or point segmentation, you can make it as point, correct? Now here I am going to select only the boxes. I want to detect which are all places. This is there. You can use any network, UNet. Okay, you can use what you call ACM detector, like that. N number of networks are there. There also you can modify also. Okay, so I'm going to use it as a this one. So now wherever number plate is there, I want to detect it. So that's what my problem is. Say I'm going to make it as num. Any name you can give. Group, nothing I'm going to make it. Now, in order to give the training, now training data is not available, no? So I'm going to make this as training data. Okay, so little more zooming option is there. Okay, so what I'm going to do is this area I'm going to make for this, correct? I want to detect this area, correct? So I labeled the first data, correct? Second data also I can label, correct? So like that, I can label it. So like that, n number of data you have, all these things, number plate only you have to show. This is the ground truth you are going to generate. And then after that, you have to, what you call, you have to save project. Okay, something, name you can make it. And then you can, what you call, like that, all images you have to give the label, correct? So this is. Now, you can export that to file, correct? Or desktop or something, and any name you can give, correct? So like that, I already made some 50, 20 images, something like this. Then I will run this code. Okay, so I already saved this. Okay, so let me give the training now. Okay. This is all this because I'm going to give that training. Little time it will take. With that ground truth only, I have saved as a file. No, here I have used it. We can see the training. So it is getting trained with this. Okay. So now it is asking me to give an image for what you call this. Nothing. Okay, so from here, I'm going to give an image. So from this unknown image, it has to detect the number plate. That is my problem. Okay, so let me. It's not detected. Oh, oh. See, from this image, exactly I detected the number plate and then cropped it. Correct. Understand now? Okay. So I made the detection of training also. I can give it using image labeler or video labeler, whatever you use, even video also you can use it and locate the thing. And now segment, next task is to just segment all the characters and then make the decisions. Okay. So let us, so any other examples? Okay, so that much only I prepared for you for this session. Okay, so thank you very much thank you for be such patient, not much bored. I feel that I made you bored too much. So before that, any doubts or something? Okay, so as a takeaway, what you can do is these things you have to, fundamental things you have to learn. So for example, so how a neural network works, what are the activation function, where it is being used, and similarly, what is its derivative, how, what you call gradient descent works, stochastic gradient descent, what is the different? Only the, what you call, the batch by, when you use batch only, we use stochastic gradient descent. Momentum means what you do. Suppose we are going to some place, somebody you are asking, then he will tell that you are moving in the same direction, the correct direction. Then your confidence will be more. Similarly, here what we do, we look back the previous movement. And then if the previous movement give you confidence, then little more you know, with confidence you move. That is moment. RMS prop means what? We have what I call, we will be using different learning rates, adaptive learning. And Nostro means what do we do? We not only look back, we will look ahead also. Because next iteration, are we a futuristic we also will make that time we use Nostro, this one. Okay. And Adam is a combination of momentum and then the validation, different validation methods you have to be familiar. Which data set, what time? Say, for example, you have to use stratified k-fold validation when your data set is imbalanced. Say, for example, if you use some medical application or something, your genuine, what you call cancer cases may be very less, and non-cancer cases may be more. So that time imbalance. So what you do is, when you make the distribution, you have to make equal distribution for both the classes. So also the regularization, different regularization methods. What is dropout? Dropout means randomly you switch off some of the nodes. L2 means it is coiled. This one means it is absolute. Early stopping, data augmentation. So these are these terms, everything you have to be very familiar. Normalization, everything familiar, and then you can make your own network. You can make publication. May God bless all of you to make good publications, good knowledge, deep learning. Any contact or something, you can contact me. Okay, I'm from GITAM University. So you can just Google it.
Thank
Anything
you,
else?
sir.
Any doubt means you can ask.
Thank you, sir.
Thank you, sir.
The floor is now open for discussion. Participants are welcome to share their queries in the chat box. Any queries from participant? Okay, sir. Good evening to one and all present here. Myself, Professor Anand, Addition Chudi, Department of CSC, Dr. MJ Education Research Institute. It is my proud privilege to propose the vote of thanks for today's intellectually interesting session conducted under the 6 days virtual faculty development program on transformative approaches in computing paradigm, machine intelligence and quantum computing. I extend profound gratitude to Dr. Justin Varghese, Professor, Department of CSC, GITAM University, Bengaluru, for delivering an highly informative and technically insightful lecture on exploring CNN through real-time, real-world example. Your presentation provided an excellent exposition on convolutional neural networks, emphasizing their computational architecture, future extraction mechanism, and real-time applications in intelligent groups. The session significantly enhanced our understanding of deep learning methodologies and their transformative role in modern computation paradigm. Once again, I extend my sincere gratitude to everyone present here. Thank you all. Sir?
Sir, okay, thank you. Can I
Yes,
leave,
sir.
sir?
We can wind up, sir. No.
Okay,
Thank you,
sir. Thank you. Thank you. Thank you.
Permission, sir?
Yes, sir.
Yeah, we can close section, sir. Sir, you
Close
can.
the session.
Yeah, thank
Okay,
you, sir. Thank you. So, any photos? Okay.
Photos taken, sir.
Okay, thank you, sir. Thank you.